Okay, here's a system classification video that explores the concept of time invariance. Okay, now words are important, and you've heard of time varying signals. Okay, anything that's not DC is time varying. Okay, but we're talking about here a system being time invariance, not the signal itself. Okay, so there's a subtle distinction. And so many times people think of the opposite of time invariance as time varying. And in fact, the Orphanitis textbook sometimes makes that distinction. It says, okay, is the system time invariant or is it time varying? I think that's sort of a loose way of describing it. I would prefer, is the system time invariant or not time invariant? Okay, so think about that. Make sure that makes sense to you. All right, so the definition of time invariance is as follows. You take a look at these two different ways of handling delays. Okay, technically speaking, these could be advances as well. So you're just going to change, shift in time either by delaying by n naught, or you could delay by a negative n naught, which would be a time advance. Okay, so there's no loss of generality by calling it a delay. All right, so in the system 1, you delay the signal first, apply it to the system, look at the output. All right. In the second system, you take the signal, you apply it to the system, and then delay the output of that system and look at that output. Okay, so if you do these two processes and it turns out that y1 of n is equal to y2 of n for all n naught and for all x of n, then the system is time invariant. So in my opinion, it helps a lot to understand these system classification ideas if I look at examples where a system is not time invariant and compare that to a case where the system is time invariant. Okay, so first of all, let's look at a situation where the system is not time invariant. Okay, so what you notice here is that I have x of n is the input to a system. Okay, and it simply is you take the signal, you put it at the output, but you put a time varying coefficient in front of the signal. Okay, so we have n, and n is the time parameter. Okay, so you'll see anytime you have time varying coefficients, you're not going to have a time invariant system. Okay, so let's see how this works out by following all the details. All right, so remember, this has to be true for all x of n and for all delays. All right, so we can take a look at one specific case, and if it doesn't meet this property that y1 of 2 is equal to, y1 of n is equal to y2 of n, then we know the system is not time invariant. All right, so let's get started. Let's take a look at x of n being simply delta of n, and you can choose any time delay. Let's make it just a 1 unit delay. Okay, so if I apply this to the first system, okay, let's think about that. All right, so we take delta of n. Let me change this to red. Here's delta of n. I delay this by 1. I have delta of n minus 1 going into the system. Okay, so how would I calculate y1 of n? y1 of n is going to be n times delta of n minus 1. Okay, and so you could plot that. All right, at n equals 0, at any time other than n equal 1, the impulse function is off. All right, so if I looked at the plot of this, I know this is going to simply be an impulse turned on at n equal 1, and the height is going to be, okay, well, it turns on at n equal 1, so you plug in, y1 of 1 is 1 times delta of n minus 1. 1 minus 1 is 0. So this would be simply 1. And it's 0 everywhere else. Okay, so long story short, this turns out to be y1 is equal to delta of n minus 1. Okay, let's go through the same process and calculate y2. All right, so again, we start with the input being a delta function. Now we apply the system. Okay, so if I take this system and I, plug in delta of n, that's going to be n times delta of n. All right, so the only place this turns on is at n equals 0, and when n equals 0, this is 0, so 0 times 1 is 0, so it turns out that if you graphed y2 of n, it would be identically 0 for all n. Okay, so you have one case where y1 is delta of n minus 1, and the second case y2 is 0. So clearly y1 of n is not equal to y2 of n. It only takes one case to prove that this is not a time invariant system. Okay, now here's a second example, and in the second example I wanted one that is time invariant. Okay, so let's prove that this particular system, where I take the input signal, I square it and time delay it and amplify by 3. Okay, so the squaring operation, we know that's actually nonlinear, but we're talking about time invariance here. So let's take a look. I'm telling you that this is time invariant, so it's not possible to just choose a specific signal and to prove it from one specific signal. You have to do this in general. Okay, so let's apply this in general. Let's calculate y1. All right, so if I started with an x of n, all right, so x of n is here. If I delay it by n naught, I would have x of n minus n naught. All right, and from there, I could calculate y1 of n, because y1 of n is you take the system, you apply it. So according to this definition, that would mean multiplying by 3, and then delaying the n value. Okay, so replacing n with n minus 2, but then I still have the minus n naught. Okay, and so, removing the parentheses, you would get 3x of n minus 2 minus n naught. All right, so that's y1. Okay, the next thing to do is to apply the delay in the system in a different order. Okay, so do the system first and then the delay. All right, so if I do that, x of n is just in general x of n. Okay, apply the system to that, and on the output I would get 3 x of n minus n naught. Delay that by n naught. I'm sorry. Delay it by 2, that's the definition of the system. All right. Now I apply this and delay that signal, delay this signal by n naught, and that would be 3x. Now everywhere I see n, I replace it with n minus n naught. Okay. And so that's y2. So the only difference between y1 and y2 is the order that we wrote, the subtraction. And since subtraction is commutative, this doesn't matter what order we go into. Then I said subtraction, I meant addition. Addition is commutative. The order doesn't matter, and so that means that y1 of n is equal to y2 of n. And this would be independent of n naught and independent of which signal x that we take. All right, so therefore the conclusion is that this particular system is time invariant. All right, so the general knowledge that you can take away from this is that if you scale something, scaling doesn't matter to time invariance. It's going to still be time invariant if you scale it by just a constant. And time shifts are preserved under time invariance. Okay, we'll do more examples of time invariance with other systems, and you can continue to develop a feel for when a system is time invariant and when it's not.